All right, in this section, we're looking at inverse functions. Excuse me. So let's say we have this function f, where when 1 goes in, 4 comes out, 2 goes in, 8 comes out, 3 goes in, 16 comes out. I'm not sure exactly how that's working, but it's our function, is what we're given. The inverse of that function, one way to think about inverse is like undoing things. Adding and subtracting are inverse operations. If you add 5 and then you subtract 5, it's like it never happened. They cancel themselves away. So inverse functions, similar idea. Not, I mean, a little more involved because a function is more than just adding or subtracting. But that's kind of how one way to think about it. So what we can do to create an inverse function, to create a function that undoes the other one, so to speak, is by simply switching or replacing or flip-flopping the domain and the range. So remember, the domain are all the input values. 1, 2, and 3 are the domain values of this function. The range values are 4, 8, and 16. So if we simply flip-flop those and say, well, now instead of the range being 4, 8, and 16, the domain is 4, 8, and 16, and the range goes from, or the domain, excuse me, 1, 2, and 3 goes and becomes the range, 1, 2, 3. So we're just flip-flopping the domain and the range, and that creates an inverse function. Instead of putting in 1, you get 4, you put in 4 and you get 1. That's the idea. That's all we're doing. Now it's going to be a little more, we're going to have to do a little more algebra, but if we're given a set of values like this, a set of ordered pairs, all we're doing is we're flip-flopping the domain and the range. So again, the domain was 1, 2, 3, the range was 4, 8, 16. The inverse function then, the domain becomes 4, 8, 16, and the range becomes 1, 2, 3. So that's the idea, and that's how we're going to create these inverse functions. Let's say we have a function that looks like this. F of x equals 2x minus 7, and we're asked to create the inverse function of this function. We're going to do the same idea. We don't have a list of values here, so we're not going to list them out because the domain we're assuming could be any real number that you can plug into this function, and so we can't list them all. Remember, f of x, that notation, that function notation, could be written as y equals 2x minus 7. Represents the same thing, your x and your y. The f of x represents the range, just like y represents the range. So sometimes it's easier to replace f of x with y. Once we've done that, which is really just a notation thing, that we haven't actually done any algebra yet, now we're going to flip-flop the domain and the range. So y is going to become x, the range is going to become the domain, and x is going to become y. The domain is going to become the range. So all we've done is we've taken what was the range and made it the domain. What was the domain and made it the range. Now, for us to be able to write this as a function, we need to get y by itself. So x is still in this new function that I've created here. X is the domain. So this is the domain, this is the range. We want to get the range by itself. So we're going to get y by itself. We'll add 7 to both sides, and we'll divide by 2. Now we have an inverse function. So if the original function was y equals 2x minus 7, the inverse function is going to be y equals x plus 7 quantity divided by 2. And that inverse notation then, kind of like before we had the function notation was f of x, the inverse function is f to this negative 1 power of x. So that's what that notation, that's that inverse notation. So instead of y, we can write that, and that'd be it. That would be the final answer. If you took a number, let's say 3, and did 2 times 3 minus 7, you'd get negative 1. And if you plug that back in here, negative 1 plus 7 divided by 2, we're going to get right back out again, 3. And so they do cancel each other out, so to speak. All right, let's look at another example here. F of x equals x squared plus 3. If you think you got this, pause it. Try this one on your own. I gave you a chance to pause it. So try it on your own, see if you can get it, but I'm going to walk through it here. So we're going to, again, I'm going to rewrite it as y. You don't have to put the y there, but it tends to be easier for me anyways. And then I'm going to flip-flop the domain and the range. There we go. X became y, y became x. And I'm going to solve for y. So I'm going to subtract 3, and then I'm going to take the square root. But remember, when you take the square root of both sides, we get this plus or minus, because it could be a positive number times a positive number, y squared, or it could be a negative number times a negative number, y squared. And so that plus or minus is going to be important. And when I show you the graphs, I'll kind of show you why that's important too. And in that function notation, then f inverse of x, the inverse function, will be plus or minus the square root of x minus 3. So remember, if you are solving a quadratic like this, and you're taking the inverse, when you do the square root, you should have a plus or minus. So there you go. That's creating the inverse function. Here's what it looks like graphically. The red line right here is the original function, 2x minus 7, and the new function, the inverse function, looks like this. That's the inverse function. What ends up happening with these inverse functions is there's some symmetry here. They're not reflected across the y-axis. They're not reflected across the x-axis. They end up being reflected across the line y equals x. So there's this diagonal line at a 45-degree angle, y equals x. And if the two functions are inverse, they will be reflected across this line y equals x. And that kind of makes sense because if you replace y and x, y equals x and y equals x is the same thing. So if you took this dashed line here, y equals x, and you flip the y and the x, it's the same thing. And everything else on either side of it is going to keep on reflecting x and y are going back and forth. That's kind of that's one way to look at it. Let's look at the other one. So here was the quadratic, x squared plus 3, that's the red line here. And the inverse function then was plus or minus the square root of x minus 3, and it looks like this. Now the plus or minus, if you were to use your graphing calculator, your TI-80, whatever, I don't believe it has a plus or minus sign. It might, I could be wrong, but I don't believe it has a plus or minus sign that you can plug into your graph. So if you just do the square root of x minus 3, you're going to get the top portion of this graph. Just the top, just the positive portion. And if you just do the negative square root of x minus 3, you're just going to get the bottom portion of this graph. But the original function had both sides of that symmetry. It had both the left and the right, which means the inverse has to have both the top and the bottom, the plus or the minus. So that plus or minus is important. And let's test that whole diagonal line idea. There's that diagonal line, y equals x. Sure enough, we have a reflection across that diagonal line. This point here has a corresponding point over here. This point is a corresponding, so we've got that reflection across the line. All right, quick joke. You're welcome to pause it. If you like clever math quips, there's a blog. Who doesn't like clever math quips, right? There's a blog called Math with Bad Drawings. They're on Facebook. They also have a blog and have just really good articles and funny, well, maybe not ha-ha funny, but kind of stupid humor math jokes. And so here we have our inverse function. I'll let you read it. All right, a function. We've talked about functions already. This is not new. You've already written this down. This is not a new page. I just copied and pasted it. A function, remember, was that for every domain value, everything that goes in, exactly one, that's important, exactly one element in the range comes out of it. So you put one thing in, only one thing can come out. You push one button on the computer, only one thing should happen. So that was a function. Now we're going to talk about a special type of function. And so let's look at a map here. This is, so maybe write this one down. So this is a function map. We talked about this before. And we're going to test first to see, is it a function? So 1 goes in, 4 comes out. So far, so good. 3 goes in, 8 comes out, 4 goes in, 4 comes out. That's okay for a function, remember. We can have 2 buttons that do the same thing. You could click enter or return and get the same result maybe. So it's okay to have, or space and tab might give you the same result. That's okay. As long as only 1 button goes to 1 place, that's okay. 7 goes to 9. So this is a function. That's fine. There's a special type of function. And the special type of function is called a one-to-one function. A one-to-one function basically says that while every domain value needs to have exactly 1 range value, every range value needs to come from exactly 1 domain value. So while this map here is a function, this range value of 4 has 2 things that came from it. So it is a function. It's a perfectly acceptable function, but it's not a one-to-one function. So a one-to-one function has to work going from the domain to the range. 1 domain goes to exactly 1 range the whole way down, like this one. And it has to work the other way, where every range value only comes from 1 domain value. Every button has 1 function, and every function only has 1 button. And that's called a one-to-one function. You won't be tested, I'll tell you right now, you won't be tested specifically on one-to-one functions. You won't be asked specifically, is this a function? Is it a one-to-one function? This comes up in different math classes later on. So it's important to know. It's also going to come up where you're going to see this. So in questions about inverse functions, it's going to use this term, one-to-one function. And so I wanted to make sure I addressed it, as this is a thing. You won't be tested specifically on one-to-one functions, but that's what a one-to-one function is. It's a special type of function. How this plays into our inverse stuff. There's a theorem here, a corollary that says if f of x, if our function is a one-to-one function, if it's a special type of function, a one-to-one function, then the inverse is also a function. Let me show you what I mean. Let's go back here. So this quadratic here, we already looked at this graph earlier. This quadratic is a function. You can look at that vertical line test. It passed the vertical line test. If we look at some values, every x value goes to a y value. There's no repeats, basically, in the x values here. So it is a function, but it's not a one-to-one function. -2 goes to 7, but so does +2, goes to 7. So while it is a function, it's a great function, it's not one-to-one. 7, the range value of 7 has 2 different values of x in the domain that go to it. And what that means for the inverse, because the original function, this red line, is not a one-to-one function, the inverse is not a function at all. It doesn't pass that vertical line test, and if you were to find some values for it, you'd see that 5, for instance, has 2 different range values that come out. And so this is not a function at all. So if it's not a one-to-one function, the inverse will not even be a function. And if it is a one-to-one function, so let's look at this f of x equals 2x minus 7, this red line here. Definitely a function, passes the vertical line test. If we look at the table of values, there's no repeats in the x values, but there's also no repeats in the y values. Every domain value has exactly 1 range value that comes out. Every range value has exactly 1 domain value that got us there. And so this red line here is a one-to-one function, which means that the inverse of that function is also a function. So if the original function is one-to-one, if it meets this special type of function, the inverse will also be a function. If the original function is not a special type of function, if it's not one-to-one, then the inverse will not even be a function. So that's one of the relationships between function and inverse function. and how this one-to-one stuff plays in. I think, yes, that's the end for section 2. It's kind of a short section, but that's it on inverse functions and creating those inverse functions.